A pinky-sized brass valve flexes a needle to meter refrigerant within 4 degrees. No sensors, no chips. This single part is why your AC and fridge actually get cold. Here is exactly how it works. Here's the problem this valve solves. Feed the evaporator too much refrigerant and liquid slugs back into the compressor, which can wreck it. Feed it too little and the coil starves, so cooling dies. Refrigerant has to be metered precisely. This valve is the gatekeeper between the high-pressure and low-pressure sides of the loop. Get this one handoff wrong and the whole refrigeration cycle fails. Start with where this valve lives. A refrigeration loop has 4 core parts, and they pass refrigerant around in a circle. First, the compressor squeezes cold gas into hot, high-pressure gas. Second, the condenser out back dumps that heat to the air, and the refrigerant cools into a warm, high-pressure liquid. Third comes our star, the expansion valve. Fourth, the evaporator, the cold coil inside, where the refrigerant boils and soaks up heat from your room or your food. Then the gas returns to the compressor and it all starts again. So the valve sits after the condenser and before the evaporator. Its job sounds almost too simple. It drops that high-pressure liquid down to low pressure. Why does dropping the pressure matter? Because a liquid that is under high pressure will not boil. Lower the pressure and its boiling point crashes, so it can flash into cold vapor and absorb heat. Without that pressure drop, the evaporator is just a warm pipe doing nothing. The valve is the exact spot in the circle where hot and squeezed becomes cold and ready. 4 parts, 1 loop. But dropping the pressure is easy. Doing it by the exact right amount, moment to moment, is the hard part. That is where the needle comes in. Now zoom in on the drop itself. High-pressure liquid refrigerant arrives, warm and packed tight. It reaches a tiny opening, a sharp needle sitting in a matching seat, leaving only a hair-thin gap. Picture a valve on a garden hose, but shrunk down to the width of a pin. The liquid squeezes through that gap under real pressure. On the far side, the pressure suddenly crashes. And here's the payoff of that crash. The moment the pressure drops, the refrigerant can't stay liquid. It flashes, meaning part of it boils instantly into vapor, and that flash chills the whole mix hard. What comes out the other side is a cold, low-pressure blend of liquid and gas, exactly what the evaporator needs to pull heat out of your air. So the needle is doing 2 jobs at once. It holds back the high pressure on one side, and it releases a controlled trickle to the low-pressure side. How much trickles through depends on one thing: how far the needle lifts off its seat. Lift it a little, a thin stream flows. Lift it more, the gap widens and more refrigerant pours through. That adjustable gap and nothing more is what the word metering means here. Not on or off, a dial. But a needle can't decide on its own how far to open. Something has to tell it. Something has to be watching. Here's the part that makes this valve clever. Something is watching, and it isn't a sensor with wires. Follow the pipe past the evaporator to where the refrigerant leaves the cold coil on its way back to the compressor. Clamped tightly onto that outlet pipe is a small sealed bulb filled with its own charge of gas. This little bulb is the valve's thermometer. It feels the temperature of the refrigerant leaving the coil, but it doesn't feel it with electronics. It feels it with pressure. When the pipe is warm, the gas sealed inside the bulb warms up too, and warm gas pushes harder, so the pressure inside rises. When the pipe is cold, the gas cools and the pressure inside falls. Temperature becomes pressure with no battery involved. Now that pressure has to travel somewhere useful. Running from the bulb is a thin tube, about as narrow as a coffee stirrer, called a capillary tube. It carries the bulb's pressure all the way back to the top of the valve. And there it presses on a thin, flexible metal disc, a diaphragm sitting right above the needle. So trace the chain. Temperature at the outlet sets the bulb's gas pressure. The tube pipes that pressure to the diaphragm on top of the valve. The diaphragm sits directly over the needle we just met. The eyes are wired to the hand. But which way does it push? Now watch the loop close itself all by itself. Say the refrigerant leaving the coil runs warm. That warmth heats the bulb, the gas inside expands, and its pressure climbs. That higher pressure pushes the diaphragm down. The diaphragm shoves the needle down with it, opening the gap wider. A wider gap means more refrigerant flows into the evaporator. More refrigerant means more cooling, which pulls the outlet temperature back down. Now run it the other way. Say the outlet runs cold. The bulb's gas contracts, its pressure drops, and the push on the diaphragm eases off. But something has to close the needle back up. Underneath the needle sits a spring, and that spring is always pushing up, trying to shut the gap. When the bulb's pressure fades, the spring wins, the needle rises toward its seat and less refrigerant flows. Less flow lets the coil warm back up. So it's a tug of war. Bulb pressure from above pushing the needle open. Spring from below pushing it closed. The needle settles wherever those two forces balance. And that spring is calibrated, meaning a technician can tighten or loosen it to set the target the valve aims for. Push harder, aim for a warmer outlet. Ease off, aim for a colder one. Here's the beautiful part. No chip, no circuit board, no code. Just gas pressure versus a spring, correcting itself thousands of times an hour. But correcting toward what exactly? So what target is this whole tug of war chasing? One thing, and it has a name: superheat. Here's the idea before the word. Inside the evaporator, liquid refrigerant boils into gas as it absorbs heat. The valve's goal is to make sure the refrigerant finishes boiling a little before it reaches the end of the coil. Then in that last stretch, the gas keeps warming past its boiling point by a few degrees. Those extra degrees above the boiling point are called superheat. Why fuss over a few degrees? Because those degrees are your proof. If the refrigerant is superheated, it is 100% gas. Not a drop of liquid is left. And that guarantee is everything, because remember what we said at the start. Liquid slugging back into the compressor can destroy it. Superheat is the safety margin that keeps the compressor drinking only dry gas, never liquid. Too little superheat risks liquid getting through. Too much means you left cooling capacity unused on the table. So the valve threads the needle, literally holding superheat in a tight band. In a well-set system, that band is often held within roughly 4 degrees. That is the 4 degrees in the title. Not a marketing number, a control target. A few stubborn degrees defended by a spring and a puff of gas. Now step back and watch the whole thing move as one machine. Refrigerant leaves the coil. The bulb feels its temperature and turns it into gas pressure. That pressure runs up the thin tube and presses the diaphragm. The diaphragm pushes the needle against the spring. The needle sets the gap. The gap sets the flow. The flow changes the temperature the bulb feels next. And around it goes, a closed circle correcting itself without pause. When your room heats up on a hot afternoon and the coil runs warm, the valve opens a hair and pours in more refrigerant. When the load eases, it throttles back. This constant self-correction is the real reason your AC and your fridge stay reliably cold, while the demand on them swings all day long. A purely mechanical brass valve, flexing a needle to hold superheat within about 4 degrees. No sensors, no chips. Just gas pressure versus a spring, settling the argument 1,000 times an hour. That is the whole trick. The gatekeeper never sleeps. So here's what to take from this. If your AC or fridge stops getting cold, the failure often isn't the big loud compressor everyone blames. It's this quiet little valve, or the bulb strapped to the pipe losing its charge of gas and going blind. When a tech talks about checking superheat, now you know exactly what they're reading. The few degrees of safety margin that prove only dry gas is heading back to the compressor. One more thing worth carrying: the smartest control in the machine has no brain at all. It's a spring and a puff of gas, outthinking a computer. One big idea to keep: a gas-filled bulb flexing a needle meters refrigerant to within about 4 degrees, no electronics required. That's the gatekeeper. But the valve is only one station in the loop. Next time we open up the compressor itself, the part that squeezes cold gas hot, and show you exactly how it does the squeezing.